Okay, well, good morning, guys. Going to do extreme values of a function day 2. We're going to finish this up. Hopefully I don't ramble on today and I can get this done in a timely fashion. But find critical points. Critical points. Remember, what are critical points? Critical points are when f prime of x equals 0 and when f prime of x does not exist. Okay? They are potential max and mins. They are potential max and mins, okay? And we're going to do this last piecewise function that we didn't do yesterday. And I will let you know that the AP board loves piecewise functions. Why? They love piecewise functions because there's all kinds of stuff going on with them that we need to know. Well, if I know f of x equals x squared minus 4x for all x greater than or equal to 0, and then it equals 1/2 x squared minus x for all x less than 0, okay, I can find the derivative of this piecewise function super easy, okay? I can say f prime of x equals, well, the derivative of the piecewise function is just simply the derivative of each piece. Well, the derivative of my upper piece here, well, that's going to be 2x minus 4, and that's for x greater than 0. And the bottom piece is going to be x minus 1, and that's going to be for x is less than 0. And just so you know, I'm just going to quick point out, this is not a mistake. Okay? Up here, it's greater than or equal to. Down here, it is not. And the reason it is not is because I do not know if that function is differentiable at 0. I have no idea. And if it's not differentiable at 0, this function's derivative exists everywhere except at 0. And if it doesn't exist at 0, I need to leave that out of the domain of my derivative, basically. Okay? So, it's not that bad. Because it's a piecewise function, okay, and because it's a piecewise function, I'm going to try to nest this up. The first thing we're going to do is we're going to look and say, hey, when's the derivative equal to 0? Well, that part isn't too terribly bad, okay, and over here I'm going to say, when does f prime of x equal 0? And I'm not graphing this. We're going to look at the graph at the end, but we're going to see if it's there. And what I can do is I can see, bottom line, this is a parabola, right? Both of these are parabolas. And what I'm doing is, when I'm looking for the derivative at 0, I'm kind of looking for on a parabola, where the heck is the vertex? Well, on the upper piece, or I guess x greater, this would be the right side, and this would be the left side, okay? Does the derivative equal 0 on the right side? Well, I have to keep the domain in mind. So remember, I'm on x greater than 0. So the only way the derivative equals 0, the only way I have a flattening when x is greater than 0 is if I can see the vertex in that part of the graph. So what I'm going to do is I'm going to take that part of the graph, 2x minus 4. I'm going to set that equal to 0. Well, that's when 2x equals 4, so when x equals 2. So when x equals 2 is a critical point if and only if that critical value is within the domain of that piece of the function. And it is. So I do know x equals 2 is going to be a critical point. Well, how about my other piece of the function where x is less than 0? I need to take that, x plus 1, set it equal to 0, and it's actually x minus 1. Sorry. And it's x minus 1, so this is when x equals 1. Now, does x equal 1? Is that in the domain of the second piece? And that's for all x less than 0. Positive 1 is not in that domain, so positive 1 will not be a critical value. And basically, graphically, what that means is when I'm looking at that bottom piece, I can't see the vertex anywhere in there. I'm not going to see the vertex of it. Okay? Now I also need to know, when is f prime of x potentially non-existent? When does it not exist? Well, I got to remember we did all this numerical stuff, and if the derivative didn't exist, well, all kinds of stuff had to happen. Okay? Now, remember, the derivative doesn't have to exist. If the function's not continuous, it doesn't exist. So really, before I even figure this out, I need to know, does f of x, are these two pieces, do they connect? Do they come together? And then the second question for the do not exist is, do they come together? If they come together, do they come together in a smooth transition, or do they come together at a sharp point? If they come together at a sharp point, then the derivative does not exist because it would be a corner. If they do not come together, and this piecewise function is not continuous, well, the derivative doesn't exist there then either. But if they do come together, and they do come together at a smooth transition, well, then the derivative would exist, therefore it wouldn't have a critical value for that side. Well, remember, rule number one is f continuous? And to find out if a function's continuous, remember, I need to know, does the limit as x approaches, and in this case, here is my only potential for a discontinuity, because both sides are parabolas, they're continuous everywhere within their domain. So the only point is, do these two parabolas come together? So I'm looking, does the limit as x approaches 0 from the right side of f of x, does it equal the limit as x approaches 0 from the left side of f of x? Okay, big question. If the limit exists and the limit equals the functional value, it's continuous. Okay, well, I already know f of 0. I can see that 0 goes into this top piece up here. I already know f of 0 is 0. Okay, well, what's the limit as x approaches 0? Well, the limit from the left, the limit from the right side, and here's my right side, here's my left side. Well, if I plug in my 0, I get 0 minus 0 equals, what do I get? 0 minus 0 on the other one, because it's actually 0 squared minus 4 times 0 on the left side, or the right side here. Okay, and in the other side, on the left side, it's actually 1/2 times 0 squared minus 0, so I get 0 equals 0. Because the limit exists and the limit equals the functional value, okay, and I should say the limit exists and equals f of 0, well, that means it is continuous. It's continuous. Well, now, because it's continuous, I know it comes together, but for differentiability, I need to know, does it come together smooth, or does it come together in a sharp point? And that's where I need to go for the next section here. And I want to see my function, so I'm trying to grab across this stuff and move it up a little bit so I can divide this off. So there we go. So it is continuous, but now the question is it differentiable? And remember, if it's differentiable, then it wouldn't be a critical point because a derivative would exist. If the derivative does not exist, the right side derivative has to equal the left side derivative. And I can find that really easy by taking the right side derivative. Well, that's going to be 2 times 0. I might as well just plug it in. 2 times 0, that's just going to give me 0 minus 4 on the right side, and the left side is going to give me 0 minus 1. So negative 4 equals negative 1. Well, the derivative on the left is negative 4. The derivative on the right is negative 1. And remember, therefore, f prime of 0 does not exist. And if the derivative does not exist, okay, that's what I'm looking for here. The derivative does not exist, that means x equals 0 is a critical point. So I have a critical point at 0, and I have a critical point at 2. So critical points occur at x equals 0 and x equals 2. And don't lose sight of what the question's asking. All this problem was asking us here in the very beginning was find the critical points on f of x. So what we did is we found when the derivative equals 0, that's the easy part. But on a piecewise function, figuring out if the derivative does not exist, that's a whole thing, okay? Especially when I have two smooth polynomials on each side, okay? Then I need to know, is it continuous? Because if it's not continuous, the derivative doesn't exist, and it's always easy to determine continuity before it is easy to define the derivative. And remember, we did have examples. I think this came back in chapter 2. We did have examples where the left side derivative and the right side derivative equaled each other. However, there was a break in the graph. So it's always really important to check for continuity first. Always check for continuity first. And all I'm going to do here is I'm going to open up. We're going to look at this graph. Here's the, whoa, not there. We're going to look at the graph. And here's the graph. Well, check it out. I have a critical value at 2. I don't want to go red. I'm going to go green. So because I had a critical value at 2, check it out. I do actually have a minimum at 2. We weren't asked to find it. And I also had a critical value where my derivative did not exist right here at 2. And I can see that that's like a little bend or a little sharpness on there. So that's what makes it non-differentiable. But notice this undefined at 0 would not be an extreme value, a max or a min. But at x equals 2, I will have a minimum. But they didn't ask us to find that yet. But they're going to ask us to find that soon. And what we're going to do is we're going to mosey on to the next page. We're going to take a little gander at what's called the extreme value theorem. The extreme value theorem states if f is continuous on a closed interval, the interval being from a to b, then f has both a maximum value and a minimum value on the interval. Now, what the extreme value theorem is talking about, in my opinion, is this is talking about absolute extrema. This is talking about absolute max and mins. So it's saying, basically, my interpretation is, if the function's continuous on a closed interval, then that function has to have an absolute maximum and an absolute minimum. And hopefully that makes sense, because if it's closed, remember this means it has endpoints. Okay? And if it's continuous, it has 0 breaks in the graph. So all it's saying is, if I have a function with an endpoint, and I really don't care what that function does, somewhere between that interval or within that, or either at the endpoints or within the interval, I am going to have extreme values. Okay? And I have an absolute max there, then it looks like this to be an absolute min right here. Now, what conditions need to be met for me to identify with the extreme value theorem? Okay, lots of people just think of the theorems and look at the theorem. Oh, it says it's got a maximum value. But all these theorems have to have criteria met before they can be used, okay? So first and foremost, f has to be continuous. And if f is not continuous, the extreme value theorem means nothing to me. I'm not guaranteed anything. And it also has to be on a closed interval, meaning I can't have open points. Well, hopefully you can see if I had an interval from here to here, I don't have any extreme values in there. I have none. My endpoints are open, therefore we can always get closer and closer to that hole. There's no high point in the graph, there's no low point in the graph. Don't forget, even if it's a constant function and the interval is closed, I'll make it closed, even if it's constant, there does exist an absolute maximum and minimum on there. It just so happens to be the absolute maximum and absolute minimum are the exact same value, but they're still there. So what conditions need to be met? It must be continuous. If it's not continuous, I don't care about the extreme value theorem. And it also must be a closed interval, meaning endpoints. It has endpoints, okay? And bottom line, when I think about this, if the conditions for the extreme value theorem are met, what the extreme value theorem basically does is it guarantees you, the extreme value theorem guarantees you an absolute maximum and an absolute minimum. If a function is continuous on a closed interval, you are guaranteed to have an absolute max and an absolute min. Okay? However, if the conditions for the extreme value theorem are not met, well, all that means is I'm not guaranteed an extreme value anywhere on that interval. Okay? But please don't lose sight of that does not mean that it will not have or could not have extreme values. They're just not guaranteed by this theorem. All right? So with that in mind, I'm going to have you to flip all the way to the bottom of your note sheet there at number 4. Just want you to peek at number 4. And what we're going to do, we're going to look at these 3 graphs, and we're going to find any absolute extreme values. And I also want to take a second, and I want you to connect and state if the conditions are met for the extreme value theorem, okay? Because it's really kind of a big deal, because it might be a theorem that you identify with on the AP test, okay? So when I'm looking at A, first and foremost is A. A is a continuous function. The endpoints I'm looking at here, the endpoints are closed, okay? And I can make that graph without ever picking up my pencil. Therefore, the EVT, the extreme value theorem, conditions are met. Okay? Now, as I look on here, all I want, I'm not asking for any extreme values. This particular problem is only asking me for absolute extreme values. And I can see I have an absolute extreme value up here at C. So x equals C is an absolute max. And I can see this endpoint here when x equals B, I have an absolute min. Okay? Well, let's take a little gander at B. Are the conditions met for the extreme value theorem? No, they're not. Conditions are not met. Why? Well, they're not met for 2 reasons. Number one, it's not continuous. And number 2, it's an open interval. Open interval. It's not closed. So as I'm looking here on this, are there any absolute extreme values? And although this has a relative maximum at point B, because it's higher right there at point B, there are no absolutes, so there are none. And then as I look at the last one, C, are the conditions met for the extreme value theorem? Well, they are not. conditions not met. Why are the conditions not met? Well, it's not a closed interval, and it's not continuous. And I would mainly state with that, if it's not continuous, I don't even care about the closed interval. So it's not continuous. But does this have absolute extreme values? Well, heck yeah. I have definitely an absolute min at x equals c. And I have an absolute max at, you guessed it, x equals a. There's my defined value. Doesn't matter. It's there. Okay? That's an absolute max, and that's where we're looking with that stuff. Okay? So now, just going to do a couple examples here, hopefully, and then turn you loose, and you can finish up your work for this whole section. Find the extreme values on f of x. Extreme values. That means find all max and mins. Meaning both absolute and local. All of them. Okay? And we're going to be looking at f of x equals x to the 3/2 power, and this is going to be on a closed interval from -2 to 3. This one we're going to kind of do backwards. We're going to look at it graphically, and we're going to figure out what we got. And then we're going to confirm our graphical interpretation with a little calculus and algebra to say, yes, we are right. So I took the time here, and if you want to type yours in, I've already graphed mine, okay? And I'm right here. Now I put the little endpoints there because I'm only really looking from here to here. Nothing outside of there means anything to me, okay? And as I'm looking here, does this have absolute maxes and mins? Well, first and foremost, if I look at the graph, I know it's a closed interval from the problem before. And secondly, is it continuous? Heck yeah, I can go from 2 all the way over to here, and I can graph that. Okay? Whoa, what did I do? Well, I can graph that without ever moving my, picking my pencil up. So what do I have? Other than blinking dots. Well, I do have, right here, I have an absolute min at x equals 0, and the absolute minimum would be 0. Okay? I have an absolute max at 3 when x equals 3, and the maximum happens to be 2.080. Okay? 3 decimal places. I have a relative max over here. Relative max at x equals -2, and the relative max happens to be 1.587. That is the relative max, okay? So now we're going to go back, and we are going to confirm that algebraically, okay? Piece of cake, or pie, whatever you prefer. So we did say, graphically, we had absolute max at 3, 2.080, with the absolute max being that value. We had an absolute min at 0, 0. Notice I'm not really stating what the absolute max or min are here. Okay, I'm just stating kind of where they occur. Okay, in this case. And I also had a local max. And that local max happen to be at 2, 1.587. Okay, so now we're going to do this algebraically. Well, in order to find extreme values algebraically, we need critical points. Critical points happen when f prime of x equals 0 and when f prime of x does not exist. That's where our critical values come from. Well, notice, finding critical values, that's calculus involved. I need to find my derivative. All right? So I'm going to kind of slide down here a little bit, not too far, and I'm going to find a derivative. And I'm going to say f prime of x actually equals 2/3 x, drop the power, negative 1/3, chain rule times 1. And hopefully everybody's looking at that. Okay, wasn't that derivative really hard to take? Well, now we need to simplify that so we can make sense of it and figure out when it's 0, when it doesn't exist. So f prime of x, when I simplify it, is actually going to equal x to the 1/3 with a 3 in the bottom and a 2 here. So that's really, or some people are going to say they need to see it like this. Really doesn't matter how you write it. There it is, okay? So when does this function, when does this derivative equal 0? So remember, zeros of a fraction are when the numerator equals 0. So you take the numerator, you set it equal to 0, and you see it's rubbish. So I don't have none. So this does not apply to this particular problem. And in the denominator, when it doesn't exist, hey, that's when I take the denominator, 3 cubed root x. When do u equal 0? Oh, I have an x here, so I can do this. Most likely, I would probably just take the cubed root, but hopefully you don't have to divide by 3 to get 0, and hopefully you don't have to actually raise this side to the third and this side to the third to see x equals 0. Hopefully you just see it right here. X has to be, oh, not x be x. Hopefully you see x equals 0 right here, so you don't have to show all this crap, because you wouldn't have to show it there. So I do have a critical value. Okay, I have a critical point or value at x equals 0. Okay, critical point at x equals 0. Now remember, when I'm looking for extreme values did not only happen, when the derivative equaled 0 and when the derivative was undefined. They also happened at endpoints, and remember, endpoints were always, and they always will be, extreme values. So I need endpoints too. Okay, so what I'm going to do is I need to find, and now if I need to actually find the maximum or minimum point, I got to come back to my original function. So I know I need to find f of the left endpoint. I need to find f of the right endpoint, and I also need to find f of my critical point to see what they are. Okay, so x to the 2/3 power, remember, f of x actually equals, doesn't it? The cubed root of x squared is another way to see that. You don't need your calculator. You don't need to waste your time with a calculator on this. So f of negative 2, well, hey, that's just the cubed root of negative 2 squared, so that's just the cubed root of 4. And at 3, that's just the cubed root of 9, isn't it? So I have the point negative 2, comma, cubed root 4. I have the point 3, comma, cubed root of 9. And I also have the point, when I plug 0 in here, I also have the point 0, comma, 0. Well, hopefully, you can reason through here, and you can see these are both positive y values. This is not. So this is my absolute minimum there. And over here, because this is higher, that's my absolute max, which makes this one, because I know the square root of 4, that's going to be a local min or relative min. I'm kind of bebopping between my terminology, which means I could make a graphical interpretation of this. I got a point here at 0, and I got a point over here at 1, 2, 3, and -2. Well, bottom line, if I said this is my cubed root of 4, I know the cubed root of 9 is a little higher, so I can tell, even if I didn't know the curvature of the graph, okay, we will be taking more tests to find out. We know the curvature kind of goes like that, and there will be testings to find out. Is it concave up, concave down in this interval? Bottom line, it really doesn't matter. We could connect these like a regular absolute value if we wanted, and we could see the absolute max, absolute min, and relative max, okay? And we're going to move on to the next problem. Now here, we're going to find algebraically, and then we're going to confirm graphically. Well, this is a cubic function. So hopefully we know this thing either looks like this or it looks like this. So I have a possibility of 2 maxes or mins or no maxes or mins, which means I have a possibility of 2 critical points or possibly 1 or none. Okay? So again, this is on the whole thing. Notice this isn't on a closed interval. We want to find maxes and mins on here. I have no interval, so now I need to find out when does f prime of x equal 0? When does f prime of x equal, when does it not exist? Okay, well, I'm going to drag these down a little bit to give myself for a little derivative room up there. And I can kind of look at this right now because g of x, this is a smooth, that's Rico-Slave in the polynomial world. And because they're always smooth as silk and curvy and nice, it's not applicable to see if the derivative does not exist because the derivative exists everywhere on a polynomial. Question is, when does it have a flattening? When is it flat? Possibly flat. Well, g prime of x is going to equal 3x squared minus 12. So then I can take that derivative, 3x squared minus 12, set it equal to 0. Well, I'm a factoring freak, so I'm going to pull my 3 out and say x squared minus 4 equals 0. And then I take that and say plus 2 and x minus 2 equals 0. So I can see I have a critical value at x equals -2, and I have a critical value at 2. Okay? This wants me, these problems are asking me to find the extreme values. To get those, here are my critical points, critical values. Okay? Now, I would want to find actually the point, because I have 2 critical values, I have 2 flattenings on a cubic function. I know it's going to look like that, hopefully. Okay? And how do I find where those maxes and mins are? Well, what do? I plug them and chug them in there. So basically, I'm going to remind yourself, and on synthetic division, I'm going to pump a 2 through here really quick, because a lot of times your placeholder, a lot of times this is going to save you time from defining a function. You can drop it. 2 times 1 is 2, plus 0 is 2, times 2 is 4, plus -12 is -8, times 2 is -16, plus 1 is -15. Oh, I just found out that f of positive 2 equals -15. And what happens when I put my -2 through there? I get a 1, a 0, a -12, and a 1. Some people are saying it's easier to plug in over there. That's fine. I'm just refreshing your memory. It's -2 is a -2, is a 4, is a -8, is a positive 16, which is a 17. So I know f of -2 equals 17. Well, isn't that pretty easy to see? Local max, local min. Okay? This point is higher than this one. So my extreme values occur at 2 and -2. My maximum value is 17. My minimum value is -15. So here's my values, right? Well, did I do it right? Well, let's check it out. Got the graph. I think I got the graph. There's my graph. And look at there. -2 comma 17. 2 comma -15. And I can see one arm goes up, one arm goes down. That's why I knew none of them would be absolutes. And we're going to do our last problem here. Of course, we're going to finish up with a piecewise function. Okay? This is a piecewise function. This is a parabola coming together with a line. Okay? And don't get all wigged out on them. They love them. Okay? But I do know critical values are when, and in this case, because it's defined as y, not f, I'm going to come up here and I'm going to say, oh, when does y prime equal 0? When does y prime equal does not exist? When does it not exist? Well, please understand the only place that this quadratic polynomial and linear polynomial, the only place the derivative might not exist is where they're coming together. It's the only place that could be. Okay? The easy ones to find are when they're 0. Because I can find the derivative of this squirrel real easy. It's 2x for x less than 1, and it's -3 for x is greater than 1. And again, that's not a mistake, because I don't know. If I'm not differentiable at 1 and I put an equal to on there, my whole problem's wrong. So I'm just leaving it off, because I don't know if it is differentiable there or not. Well, notice, this is less than, this is the left side, right? This is my left side, and this would be my right side, which means this is going to be my left derivative and my right derivative. I'm looking for critical values. Well, when x is less than 1, here's my domain for that piece, 2x equals 0, x equals 0, is that a critical point or a critical value? And the answer is yes, it is, because it fits within the domain of that piece of the function. Well, how about the other one, when x is greater than 1? Well, I take that piece of the function, -3, set it equal to 0, and I get nonsense or rubbish. Yeah, that doesn't happen, so that's not a critical. So x equals 0 is definitely a critical point. Now, I need to see, does it exist? Okay, I got to check here. So first and foremost, I've got to look for, is it continuous at x equals 1? Well, that makes me check the limit as x approaches 1 from the right of my, just going to leave it as a y in there because that's how it was defined, of y. Does that equal the limit as x approaches 1 from the left of y? Well, are my limits the same? I can see when I plug 1 into, I can see y of 1 equals -1, right? Well, what's my limit? Well, as I'm coming in from the right side, my limit is going to be -3 plus 2. And this is checking to see if it's coming together. And the left limit over here is going to be 1 minus 2. So I get -1 equals -1. So it is continuous there. And because it's continuous, that just means it comes together. Now I got to see, does it come together sharply or smoothly? So now I need to compare, because now I know it comes together, so it's not a discontinuity. If that were a discontinuity, if it did not come together, well, I could automatically say x equals 1 is a critical value. Now I got to check, does the left derivative equal the right derivative? Well, all I got to do to check differentiability is come into my derivative. Well, what is the derivative at 1 on the left side? Well, it's going to be 2 times 1, so that derivative equals 2. And on the right side, that derivative is always constant, it's negative 3. So because the left derivative does not equal the right derivative, that means y prime of 1 does not exist. What does that mean? That means x equals 1 is a critical point. So I have 2 critical values, okay? And then what am I going to do? I'm going to evaluate these two, okay? So now I want to know what the heck is y of 0. What is y of 0? Y of 0, 0 is going to fit into this guy, right? So y of 0 equals negative 2. And what is y of 1? Y of 1, ooh, that fits into that same piece. Y of 1 is negative 1. Well, because I can see this is a upward opening parabola, right? And I can see the vertex is at 0 off of my derivative. So I know that's going to kind of look like this. And this is a line with a negative slope, so that's coming down. What does that mean? Ooh, yeah, hopefully that picture makes sense, because I can see my, right here, this is going to be the vertex of that parabola. So this is kind of what my graph is going to look like. And I can see here at 0, this is the vertex of that upper piece. So that's a relative or a local min. And then y equals 1, well, that was a little bit higher because that was at negative 1. Well, that means this is a local or relative max. So there we go. My points, my extreme values occur at 0, negative 2, and 1, negative 1. The actual minimum is negative 2. The actual maximum is negative 1. Did I get that graph correctly in my thought process? I don't know. I've made mistakes before. I think I probably made a couple today already. And there's the graph of that piecewise functions. Well, I'll be a dirty bird. Look at that. Look at that. Whoa, 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 whoa. Didn't want that. Need a color, children. Need a color. I can see I have a minimum at 0, negative 2. I have a maximum at 1, negative 1. Isn't that where we said they were algebraically? I think so. Why, yes. Oh, crap. I did that again. So, fancy way, 1, negative 1. We said that was a max. And at 0, negative 2, we said that was a min. Well, isn't that fancy? Isn't that fancy? So, I'm done. I was going to do something fun, but I'm not going to do anything fun. So, have a good rest of your day. And if I can find it, talk to you later.